soon. Anyway, it did. Okay, so we talked about that the second central. So, for example, the second, third. In general, moments are used to characterize the probability density of a random variable. For example, the second, third, and fourth central moments. I think we talked about these in the previous session. They are intimately related to the shape of the probability density function of a random variable. The second is a spread. The third is a skewness. Okay, I think we talked the bias from left to right. And the fourth, it's a measure of flatness. So these are essential. And then we have the spread of the shots. It's the Gaussian probability function. So the probability distribution function, this is what we wrote also on the board. This is slightly different from what I wrote here. So we wrote here together 2 sigma square. So it is, we're not losing much essential here. So in the exponential term, we have x minus m, where m is the value around which the distribution is centered. And we're divided by 2 sigma square, or sigma square. But this value of 2, we're going to see when we do some experiments or some exercises to see what 2 sigma square versus only sigma square mean with respect to each other. Now, this is the Gaussian probability distribution function, the PDF. This is what we observe here. So these are normalized, both sides, several random variables. So I think the most essential part is we already covered it. So I strongly suggest you go over those components. Now we have a very important concept, which is now we discussed the variance, okay? And now I see here talking something about the covariance, because here we can observe 2 different variables where we have x minus the mean of x to the power k times y minus the mean of y to the power q. And we are integrating these 2 variables. But now imagine for a moment if we have discrete data points and the variance, let me see what we have here. So we are trying to determine the correlation coefficient. Now the correlation coefficient is just, now we can, so let's try to, so the variance, it's equal to x minus x average times x minus x average. This is the variance. The covariance, this is equal to x minus x average times y minus y average. So here we can observe that this is the variance, this is covariance, because the covariance, it measures how much 2 different variables that could be correlated with respect to each other or not correlated, and we want to observe how they covary. To be 2 variables that covary together or that have a high correlation coefficient are data points that go like this. So here we see that x and y, with the increase in x, we observe also an increase in y. So we have a strong correlation, and covariance is a high value. But if the values of x and y, they are randomly distributed, the covariance will be smaller. Now, the correlation coefficient, so we can call this one correlation coefficient. This is equal to covariance. Sometimes I forget this formula, okay, but I think it's sigma x divided by sigma y. So this is the correlation coefficient. At least it should be this way, because the correlation coefficient, it should have no unit, and here we have the units of x times the units of y. And the correlation coefficient should be just a number, which is a number from 0 to 1, from 0 being no correlation at all, 1 being perfectly strongly correlated. And then we have to remove the units, so definitely this should be dividing this product divided by the sigma, the standard deviation in x, divided by the standard deviation in y, and something similar you also observe in this slide. So apparently, yes, I think the second line on this equation, it is denoting that the correlation coefficient is equal to Cxy, which is a covariance in these two variables, divided by the respective sigma, divided by the respective distributions. We have the multivariate Gaussian density. This is a little more complex concept, which is not, I cannot come up with a possible application of this for the moment, but I can come up with an application of what we are seeing right now. Covariance matrices are real. Okay, covariance matrices, these are very important concepts, and these covariance matrices, we try to determine the major axis in multi-dimensional data distribution. Now, this is a beautiful part of advanced linear algebra, which some of you can take in the second year, because there is a course called Advanced Mathematics for Computer Science. In there, we cover advanced concepts of linear algebra and the applications in high dimension data sets, but starting also applications of these principles in image analysis. So this covariance matrix, this is, so we might see them there. Now here we have a multivariate Gaussian density. It's something like, it is easy to see a three-dimensional structure of a bell. Okay, so I'm trying to see some object here, which I can show, or no, I cannot see something very available, but you can think this one as a bell. So we don't see bells often right now. When the class is over, we don't ring it anymore, but it has a bell shaped, and now a bell shaped, it's a Gaussian distribution in 2 dimensions. Okay, what we draw here on the board, we just drew Gaussian distributions or normal distributions along only one dimension. We have linear transformation of random variables. Okay, this is the last slide, review of probability. So please go over this review of probability, especially for the aspects of the moments. Now, let me see what essential elements we have in this linear systems. Okay, this is for linear systems theory. Now, this linear systems, we're going to see that many operations that we conduct onto the images, they are linear operators. And the moment that we say that they are linear operators, we can represent them using linear algebra. So we can simply denote even complex functions with a matrix. Okay, even Fourier transform, it is a linear operator, which means that we can denote it as a summation, or let's say a matrix operation which is applied on a vector. This is the most general aspect of defining linear operators. And linear operators, they have several properties, where one of them could be the following. So f1 plus f2 on x, this can be equal to f1 of x plus f2 of x. Or derivative is a linear operator. Integral is a linear operator. Okay, so linear operators, they are also interchangeable, which means that it can be. So let's see here, an operator is called linear one in case if the linear operator h is applied on function fi and fj, that means that the linear operator h can independently be applied onto a function fi and independently be applied on function fji or fj, and this defines a linear operator. So we see some more, so there is a property of additivity, which we saw it in the previous slide. Linear operator can be time invariant if it satisfies some principles. And now, linear. Now, here we see integral, which is the, in principle, this is also, we know that in integral, it is equivalent to summation. Okay, and now we are going to see that in system where the data sets are not discrete, we can often apply an operator to a specific function. And for example, this can be a filter. A filter, if it is, we can find the effect of a specific filter on a signal by conducting sometimes difficult analytical integration of complex functions. The same thing can be done also when we have an image, but now we don't have complex integration of a kernel or of a filter on an image, but we use element-wise pairing of the kernel of the filter with the image. Now, when you say element-wise, we have a matrix where on each of these rows and columns we have the pixel intensities, and we multiply these with some kernels. A kernel, it's a matrix which can be 3 by 3. They are small kernels. A kernel is just a small matrix, and often the summation of all of the numbers that we can find in a 3 by 3 matrix, or 5 by 5 matrix, or 7 by 7 matrix, the summation of all of these elements should converge equal to 0 for reasons which we're going to mention again later. And these kernels, when they are applied onto an image, which is a discrete values distributed across a large matrix, we multiply them 2 by 2, and then we just add them up together. And these are linear operations with the filters. Now, here we have some more discussion on the linear systems. But I want to see, okay, so we don't have much that I can strongly focus onto. Okay, so let's pass this one again, and we may want to go. And so these were elements that you may have to go over those, or elements that you need to know during your work, not only with image processing, but other beautiful related with area of image analysis or image processing. Now, whenever we have, since we're discussing with imaging, an important aspect is the image acquisition. So, which is the ability to have a camera, and this camera should be able to detect an object that is in front of the camera. And the best similarity that we can construct with a natural biological construct is human eye. And the human eye, it has the construction as shown in here, and we have a lens. The lens absorbs the light goes through, and this lens, it absorbs around 8% of visible light. Actually, I don't remember what spectrum it absorbs, but it could be very useful if the lens absorbs the ultraviolet light, because UV, it is dangerous for our health, and the UV, it's absorbed most of the time by glass. So if you are sitting in your room and you have the window, and the window is closed, but the curtains have been taken away, light can come into your room, but UV wavelength of the light, it is completely absorbed. It is good because it will not cause cancer on our skin cancer. But if you go to the sea or to the beach, you are not protected anymore by some glasses. You are out in the sun, and you have no natural or artificial absorber of the UV light or ultraviolet, so that might cause some damage on our skin. Now, I never thought, probably I know, but I don't remember it right now. I wonder what part of the spectrum the lens absorbs, but this could be something that you can check it, and you can come and tell me, or you can tell each other. Now, we have a lens which absorbs around 8% of visible light. And again, if it absorbs visible light, that means that it might not absorb invisible light, which means that, let's say, wavelength in the order of 1000 nanometers or 2000 nanometers, it's out of the visible spectrum, but there are spectrums which we can easily communicate, and they might bring information to our eyes, but we cannot perceive, we cannot operate with those because we have a visible spectrum somewhere between 400 and 700. Now, the human eye is composed of rods. Let me see. I think we can see more information here. So the normal angle with respect to the incident light, it's at 0 angle. We have some, let's say, some regions where we can find rods and cones. So the rods and cones, they are small constructs or small regions that have nerve endings, and the number of rods and cones is something in the order of 10 to the power 8. So we can have 10 to the power 8 rods, and we can have 10 to the power 6 cones, okay? 10 to the power 6 cones, it's in fact something like an image which could be 1000 by 1000. So 1000 by 1000 pixel, it is 10 to the power 6 pixels that we can see in a traditional image. So these are, let's say, what the cone can do. Now we have some more. Now the cones, they are simple, they are similar to pixels connected to amplified circuit components, okay? So in fact, the way to construct a pixel is that we have to be able to determine an area where if a photon is incident on this area, we want that to be separated from the neighboring region on the camera, so that we can have a high resolution in space, a high spatial resolution. So if we want to detect a hair in Fiefloco, hair, we put it into a microscope, and we wish so that the light is projected onto different pixels so that we can detect the edge of a hair. And these pixels are called CCDs, which is a type of the camera. Now they're called CMOS. And CMOS, when compared to the CCD cameras, the only major difference is that CMOS, they spend less energy. This is the most important aspect nowadays. So once you make a product which is comparable to the previous one, and sometimes it can even operate worse than the previous one. But if it spends less energy, then we go for it. Traditionally, we can sacrifice performance for the sake of energy expenditure. And decreasing the energy expenditure is not only because we want to save money, but it's also because of the fact that as the electronics is getting smaller and smaller, these smaller components, they have a maximum amount of energy that can absorb. So we want to decrease this amount of energy. Otherwise, these components will get very hot. We have some cameras here that sometimes we do for our research here in the lab. If the camera stays on for like 10-15 minutes, if you cannot touch it. If you cannot touch it, that means that it's something over 60 degrees Celsius, because that's how much human hand can withstand. But this can be detrimental for the camera or for the CMOS. So we may need to use a cooler, or let's say air cooling. But one of the reasons why that can happen is that we're spending too much energy per unit area. And these pixels that we have, that we can traditionally buy, the best pixels, they have for a very reasonable price, because maybe pixels can get smaller and smaller. But for a reasonable price, we can get a pixel area 1 micrometer by 1 micrometer. Okay, so 1 micrometer by 1 micrometer, you pay only 200 euros. That's all you need to pay. And 1 micrometer by 1, that means that you can have 40 pixels. Okay, so you can have 40 pixels, and you can take a hair, Fiefloco. You can send light, so you can send light source. Light source, it travels in the way of photons, and this has a thickness of 40 micrometers. So we can see it, but it is micrometers. And if you use no magnification at all, okay, so normally we may want to magnify objects so that we can see those, because it's a small object, but with no magnification, this hair is going to block 40 pixels on a camera. And if you have 40 pixels across for a single object, you can easily detect an edge, okay? And you can detect the other edge. And here you can see the let's say, in this case, the human hair. Or if you want to observe, now we are considering the extreme case when we're trying to do microscopy. And when we say that we're trying to do microscopy, we are in the region where we want to magnify objects. So let's assume we have a cell. Jeśli jest a cell, it has a dimension around 10 micrometers. Even if you do not, or even if we don't use any magnification power, we just project the cell onto the pixel. If the pixel is 1 micrometer, you can easily calculate that the projection of the cell, of this super small biological component, it will block 10 pixels onto the camera. Then what you can do is that you can now look at the monitor of your PC and you can count, you have 10 pixels across. So if you can count them, that means that it is easy for you to determine the edges of this cell. Okay, so if it is round shape or square shape, if you have 10 pixels, you are good. You might need 5, it's also kind of enough. 3 is too less because you need 1 pixel for the edge, another pixel for the other edge, and 1 pixel showing the inner components. This is not perfect, but having 10 pixels overall, that is some good size. Now, where we are discussing this is that we have to know to some degree what could be the size of a commercially purchasable camera and the biological system camera, which is the eye itself. Now, eye is it's a very good camera because it can have 10 to the power 6 cones, which would be equivalent to having an image 1000 pixel by 1000 pixel. But we have also 10 to the power 8 rods. So we have 100 times, which means that 10 to the power 8 rods, we have a better resolution than 4K. So nowadays we have this 4K cameras, 4K TVs, which are out with relatively high prices. Human eyes, it has a resolution of larger than 4K. And 4K is not really something huge. It's just 4000 by 4000. So we are used now with 2000 by 2000. 4K is just twice that. It's not that much. But the number of rods in a human eye, it is really a very high resolution. And assuming that human eye, it has a diameter of 20 millimeter, you can now check what is the size of a rod. So you have an area which is 20 millimeter by 20 millimeter. The area, it is 20 square because it's proportional to the diameter square. 20 square, it is 20 square is 400 millimeter square. So let's use millimeters. So it is 400 times millimeter square. And now we may want to determine what is the area of each rod. The number of rods is 10 to the power 8. So if you divide this one by 10 to the power 8, we remove these two, we get 10 to the power 6. And then we have to multiply 1 millimeter. Now this, I'm sure that you are, if you pin the camera, you can watch this, otherwise no. But so on the recording, you might not see this, but this is 1 millimeter square divided by 10 to the power 6. We multiply 10 to the power 3 micrometer per 1 millimeter times 10 to the power 3 micrometer divided by 1 millimeter. So millimeter squares, they are cancelled out. So we get something like 10 to the power 6 micrometer square divided by 10 to the power 6. So it looks like in our human eye, the area which is occupied by a single rod, it is 1 micrometer by 1 micrometer. Okay, so apparently this is really small. So this is comparable to the best pixels that we can construct or that we can manufacture. Okay, so now let's move ahead. So whenever we have a camera, we have human eye. Traditionally, what the human eye, what it does, there is a question. What does human eye do? Does it magnify or does it demagnify? What do you think? The human eye, it demagnifies, so it's not magnifying anything. It's not a microscope. Human eye, an object which can be as high as 15 meters, it has to project it down to a region which is in the order 2 to 3 millimeters. So it's simply doing demagnification. So it's like doing something not bad, but it's doing something bad. But now what can happen is that if you take out of course, we're just discussing principle. So this lens, the equations that can be written for this lens, what they do is that they take this 15 meters, they project it down to 1 millimeter. Now, the same equations can also be written for the inverse. What I mean for the inverse, this means that this 1 millimeter, which is at the side of the retina, it's now projected to 15 meters. So what this could mean the following. We can take a human eye, let's say we take a cyborg, and then the lens that they have, we can rotate it on the other side, and now the lens will do magnification. So now the lens will be a microscope, because you can show a component which is 1 micrometer, it is going to magnify it 1,000 times, so it will be projected onto the retina, filling it all over, and we are going to have a beautiful view of an object as small as 1 micrometer being magnified by 1,000 times, only because we can reverse the lens in the human eye. Okay, but we cannot do it, but for cameras we can easily do it. So you have the camera of your cell phone. What you can do is just you break it, open it up, rotate the camera, the lens, which is a glass something, or let's say like something like glass components, rotate it upside down, you get a microscope from your cell phone. Now, there is actually, when we analyze an image, there is this issue of the brightness, or the different sensitivities for brightness. Now, there is in this graph, we just show here the subjective brightness sensation as a function of the intensity. So when the light intensity, it is very high, we observe different domains for the, let's say, for the brightness. And here, this is the region that falls into human eye. It's something, the logarithm is from -3 to -1. So human eye, from this graph, we should read something for values smaller than 1. This is scotopic domain, okay? And now the rest is for highly sensitive cameras, but even when the intensity is too high, there is also an upper limit. Even these components, they do break. So if you shine a laser into its MOS, a camera, if it absorbs more energy per unit area, you are going to burn it. So you can do an experiment. You shine a very high powerful laser into a component. That means that it has a high the logarithmic value of intensity. It would be too high. You can simply break it. The same thing can happen also for human eye. That's why at least this domain from -3 to -1, that's what human eye has. And now, in order to measure the human perception regarding the possible changes in intensity as a function of overall brightness, this is a basic experimental setup. So in the previous session, we had some squares. We were trying to see them, plotting them using MATLAB, and we noticed that we could simply not see those edges. We could not see a square, okay, because the pixel intensities, they were ranging from 0 to 16 for one of the images, and the other one was from 0 to 32, I believe, and still from 0 to 32, human perception was null. We could not perceive it. Computers do perceive it very well. Computers are very nice, so quantitatively, they are good at every domain, computers. But human eye, human perception, it does worse. For this, we can plot typical graphs, which is these are the Weber ratio as a function of the intensity to analyze, let's say, the changes in the gradient of the intensities. Now, another thing that we can add regarding the intensities is that Low level of illuminations, these are carried by rods, and the high level of illumination, this vision is carried by the cones, which are in human eyes. And here we have some graph of the human perception, which can happen if we see a gradient of intensity, as shown here in the figure. For example, we can have actual intensity which is changing as a graph in the middle of the figure, but perceived intensity by a human, it's something slightly different. So we can observe, we can perceive a higher gradient where the intensity is changing. Now here we have also some other examples of simultaneous contrast. Now the inner squares, they have the same contrast or the same intensity, but they appear progressively darker because the human perception does automatically calculate a contrast with respect to the background. Now here we have some traditionally optical illusions that can happen for humans. So normally you can draw a square in the first image A, we can draw a circle in the second one. We can also compare the length of different rods which are shown at the bottom, or whether the rods are parallel or not. Now here we said, now this were, so far we just discussed about human perception when we analyze different image components. Here we can observe the wavelength or the electromagnetic spectrum that or the electromagnetic spectrum which is used for image acquisition and for image analysis. Now, in order to have high resolution, high spatial resolution, which means that if we want to selectively separate two, so you have, if you want to zoom in and you look at your hand, if you want to detect two different components, to separate them, we have to have a high spatial resolution. The high spatial resolution, it is a directly linearly dependent or inversely dependent with respect to the wavelength, which means that if we use a shorter wavelength, that means that we have a high resolution. For example, visible spectrum, which you can see this one somewhere in the middle of this slide, the visible spectrum is somewhat between 0.4 micrometers to 0.7 micrometers, which is from the blue to the red. Now, 0.4 micrometers to 0.7 micrometers, that means that if we use a microscope using visible spectrum wavelength, we can observe a resolution down to 0.4 micrometers. Okay, that one we can do. But if we use a radio wave, radio waves, they have a length of 1 meter, okay, or 100 meters. So if you have a wavelength of 100 meters, it is impossible for us to detect a microstructure or something which is microscopic. Now, there is an inverse relationship between the frequency and the wavelength. The frequency is always equal to the speed of light divided by the wavelength. So, for example, if we have here the wavelength, which is 400 nanometers, 400 nanometers, it is 4 times 10 to the power minus 7. The speed of light, it is 10 to the power 8. So 10 to the power 8 dividing 10 to the power minus 7, that means that the frequency should be somewhere in the 10 to the power 15 hertz. So this is how you can read these graphs here. So the most immediate relationship that you can construct between the frequency and the wavelength is that the product between these two, it's a constant number. So frequency times wavelength is equal to 3 times 10 to the power 8, or 300,000 kilometers per second, 3 km per second, or 3 times 10 to the power 8. This was, and now this is the wavelength. There is also a direct relationship between the frequency and the energy of a photon. Now here we have the graphical representation of a wavelength of a photon. Smaller than this wavelength, which is from crest to crest, that means we have a higher resolution if we use it for image acquisition purposes. Now, here we have the sensing elements which can be used for image acquisition. We can have line sensors or array sensors. Now, the cameras that we use, they are all array sensors, which is like this graph at the bottom. But each pixel or each component on these array sensors is composed of a filter, which filters some part of the energy. It has some sensing material. It has some power, it has some housing. It has also a lot of electronics which amplifies the signal that drops in. When you see the signal that drops in, imagine now there is a photon which hits this sensing material. This, what we are discussing for this slide, this is not something which is fundamentally essential for computer engineering students, but it is fundamentally essential for electronics engineering students, because electronic engineering students, they have a better understanding. They have taken all the necessary courses to understand that once a photon falls onto a specific material, it is going to excite some more electrons, and these electrons, they fall into a photomultiplying tube, and this photomultiplying tube produces 1000 electrons for each incident electron. So the signal which is incident because of some electrons which are falling, this is going to be magnified or multiplied by at least 1000 times. Okay, so this is how this is constructed, and the electronics which should be associated with each pixel, which can be as small as 1 micrometer by 1 micrometer, which is very small. The electronics is challenging, which also limits our capabilities of producing smaller and smaller pixels to have a higher and higher resolution. So let's move back again. So now, as we said, we can have light acquisition systems which have a line sensor, array sensor. Array sensors are better for images because we also view in 2 dimensions, or the projection in 2 dimensions. Here we have another way to detect where the sensor can be linear, but they can sense something on a film which can be rolled over a cylindrical rod. Now here, these sensors, we can put them into different geometries, and so you can assume these as if you are scanning, you are having a line sensor which can be like this line, and you are scanning on the top of some region. So, and then you are obtaining a 2-dimensional image. This is the possible image acquisition units that we can use. Now we have also other types of sensors which can be used as this image at the bottom, where there is this cylindrical circle where we can have a linear motion which moves in and out. Okay, so these types of scanners, these are used for medical scanners, where the image that is acquired, we cannot even see it. Okay, so what we mean with this is that we hope nobody goes there, but there are these CT scans or MRI scans where people can do a very high resolution scanning of the lungs, especially if somebody has COVID-19. You can take an X-ray scan, or you can take a much higher resolution scan, which is similar to this design here, where a person goes into a tunnel, let me call it a tunnel, I cannot find a better word, but all the light source which is going to interact with our lungs and is going to be reflected backwards will be projected on this 2-dimensional structure, which is going to look like this. Okay, so the image, it will be projected on the inner surface of this, but afterwards we need to apply image reconstruction algorithms so that from the projection on the inner side of this element, we need to reconstruct this from a 2-dimensional printed here, but which was like this. We want to construct a 3D imaging, and for this very high advanced image reconstruction algorithms are used, and that makes possible for us to have a very detailed diagnosis of 3D objects. Now here we can see an example of digital image acquisition construct. We have a scene, we have an imaging system, and the image is projected into an imaging plane, and the output digitized image, it looks like as it's shown is in there in a pixelated manner. But in order to obtain an imaging for an imaging system, we should have also an illumination energy or illumination source, and the wavelength of the light source used, it is directly related to the resolution. Now this here we can have, so these 2 graphs, these 2 slides are important because here we observe what we can observe here is if we have a line between A and B, the background, apparently it is white. If the background it is white, just to the left or to the right of the point A, we have high intensity. This could be the brightest spot. And right at the edge of at the object, which is darker than the background, the intensity drops. Then as we move from A to B, we observe that the intensity is increasing. It's still increasing. Apparently the highest contrast is at the edges. And just before we go to the other edge, closer to B, the intensity drops a lot. At B, the intensity is still high again. Now, this sampling that we see, actually, so as we're scanning along the line A and B, we have this idea of the sampling. So digitizing the value of X and Y, so imagine now, this is a two-dimensional structure, and we're trying to get readouts as we're moving from left to right. This is called sampling. So digitizing the X and Y, this is called sampling, but digitizing the fxy, which means the intensity, this is called quantization, okay? So that's why you see here the sampling is along the x-axis and y-axis, and the quantization, it is along the z-axis, which in fact it is the depth of the image. And a good example regarding the quantization, not example, but we can observe these. So these are quantization levels, which so the quantization levels here, they are from 0 to 1, which we can observe that as we move, we can observe that the intensity in the y-axis, it is changing. So that we can call this one as a quantization of the intensities. I should not be looking at this, but we can go back to here. Okay, then this is image projected into an array. This is an example of how a letter D, which is shown here, it can be seen, we can plot it, which in this case, it can be plotted using imshow. So insert text box. This can be used using imshow in MATLAB. This could be of an image. And this could be insert, where is this? Text box. This can be plotted as using surf-L of the image, which shows the three-dimensional structure, which shows that, not structure, but we can say that if the intensity is higher, we see it higher in the y-axis. Okay, then we move again here. So we observe here that whenever we have an image, we have actually this slide is not telling much, just telling us how the image can be distributed into an X and Y array. And whenever we have images, we have some issues which might come up, where one of them could be the saturation. And the saturation means that if we have a maximum possible intensity that we can acquire, we don't want too many intensity gradients right at the upper boundary, which we can observe, okay? So saturation is that the intensity might be changing over there, but the level, we might have saturation so that we will not be able to observe anything. Now, this is something regarding the size of an image as a function of n and k. And k, in this case, it is going to be equal to, so n, it's something which goes from 1 to 10 to the power 3. So this immediately means that n, it corresponds to the number of pixels on an image, okay? This is what n is, but then we have also the value of b, and in this case, the value of b, it would be the number of bits, okay? So we did some examples in the previous session where we used 8-bit images, which means that the k would be equal to 8. And we can calculate for an image that we can acquire, we can calculate how many megabytes it is, which is going to be equal to b divided by 8 times 10 to the power 6. So in the x-axis, we just show the number of pixels. On the y, we observe how many megabytes we get if we have an image which is 1 bit, 2 bit, 3 bits, 4 bits, 5 bits, and so on. So if you have an image which is 1 bit, that means that we have 2 levels of intensity, which is 0 and 1, which means that we have black and white image. If you have 2 bits, that means that we have 2 to the power 2. That means that we have 4 different levels of quantization. So now we can have a higher range of quantizing, value intensity changing from really dark to really bright. And so we have 4 different levels, 3 bits, that means that we have 2 to the power 3, that makes 8, and the pixel values will go 0, 1, 2, 3, 4, 5, 6, 7, and so on. Now, this is one way how we can scan a 2-dimensional image. It's not that difficult, and in terms, so if we go back here to MATLAB, it's just, we can just represent this as a, where is this? So for example, let's see, here we have a matrix A, and the element A, the 6th element, is in the first column, it's 11. The 7th element here is equal to 12. The 8th element is equal to 2. So traditionally, in an image, often we count column by column. So the first element is 6, the second one is 2, the 6 is 11, the 7th is this 12, and then we move down, then it's 2, 6, 4, 11, and so on. So A13, now this is not something very technical. A13 is equal to 12, it is this 12, and the next one should be 3, which means A14 is equal to 3, and so on. Okay, so now, but what is essential to notice here is that if we have a large number of pixels, we can calculate, we can divide it by by one of the dimensions, and if we find when we divide, the quotient is going to determine where the column is, and the remainder, it is going to determine which element it is. Now, we can also look in here, so matrix A, it's here. Then if we want to say, we want to find, let's say, A, we have 36. So 36 divided by 7, this is equal to 5, and the remainder is going to be equal to, the remainder is going to be 1. So 7, if we have a matrix, in fact, here we have, we can divide this better by 6, because we have 6 rows, and if we divide, if you are going to write any code which is going to apply some filters on images, you have to be aware of these, that to determine actually with which pixel you are really working on and how you are going to apply this filter. Later on, we're going to study two important applications that we can do with images, which can be the correlation and the convolution. And these two are two operations which are kind of inverse of each other, not really inverse, but they are applied in an opposite manner with respect to each other. And if we are going to write the codes of these, we need to know how to correctly write down the images. Now, we can stop here for the moment. Do you have any question so far? If not,
no, Professor.
Okay, thanks for